Hello, everybody. I hope everybody is doing well. My name is Ali Shojaizadeh. Today, I'm going to present our research that we did. It's the GIP-SWMM, a new green infrastructure placement tool coupled with SWMM. This research is a part of a teamwork project that is a collaboration between South Dakota School of Mines, Colorado School of Mines, Georgia Tech, University of California, Berkeley, and the Nature Conservancy, and funded by the EPA. Outlines of the presentation we have. It's first, I'm going to talk about why do we need green infrastructure placement tools. After that, I'm going to talk about the disadvantage of the existing approach for the green infrastructure placement, conceptual framework of the green infrastructure placement tool coupled with SWMM, and I will go through a case study and the result of, I will show the result of the case study from green infrastructure placement tool coupled with SWMM, and at the end we have the conclusion part. So why do we need green infrastructure placement tools? Billions of dollars are spent on implementing green infrastructure to have functional, healthy, and vibrant communities. So this huge amount of money is spending in most of the countries to implement the green infrastructures. How to reduce this amount of huge costs? We need effective design and placement of GI through optimization that can reduce this huge cost. And usually GI placement, the green infrastructure placement tools, they use multi-objective optimization that are capable of evaluating trade-offs between cost, stormwater runoff quantity, and quality. Some of these new approaches, they use the genetic algorithm and scatter search optimization programs. And these methods, I can say, like, for example, these methods these existing tools that are such as Sustain, Greenplan IT, RSWMM Cost, and Ostrich SWMM. What are the disadvantages of existing approach? So these approaches, they're simultaneously solving for multiple objectives, and this, because of this, it can restrict the convergence of the tool. All the possible solutions in the feasible objective space are local solution, not global, and just the Pareto optimal front is the global solution. And these tools, the existing tools, they need to solve for the entire feasible objective space to find the Pareto optimal front. And because of that, they are time consuming and they are computationally intensive. We applied the linear optimization in green infrastructure placement tool coupled with SWMM. And why linear optimization? Because it reduced the running time, saved the cost, and you can use any computer to run. It needs fewer input data parameters, and it will not fall into trap of local minimum or maximum. And because of that, it will improve the convergence. In this slide, I'm going to talk about the conceptual frameworks of the green infrastructure placement tool coupled with SWMM or GIP-SWMM. The tool includes 4 component modules that integrated into one tool. The first one is a module linking a SWMM with optimization module. And second one, we have a constraint such as target water quantity or quality. And the third module is a green infrastructure that it has two sections. The first one is we develop a new module to calculate the GI performance, and the second part is a cost module of the green infrastructure. And at the end we have an optimization module for placement of the GI to meet the target water quantity and quality requirement. In the next slide, I'm going to talk about the green infrastructure performance, how to calculate it, how we calculate that, and the cost modules of the green infrastructure. So green infrastructure performance can be based on the flow or the pollutant. In this slide, I'm talking about how to design the green infrastructure based on the flow, and the next slide I will talk about how to calculate the green infrastructure performance based on the pollutant reduction. For the purpose of sizing, the green infrastructures categorized in two different groups. We have infiltration-based GI, such as bioretention and the permeable pavement, and we have a storage-based GI or green infrastructure, such as dry pond and wet pond, and mass balance approach applied for all types of green infrastructures. This part is a design of green infrastructure based on the pollutant removal. Again, we classified the green infrastructure type to two: infiltration-based and storage-based. For infiltration-based, such as bioretention or permeable pavement, we are using the decay rate, and we design the GI based on that. For the storage-based, we group based on the pollutant type. We have colloid pollutant and dissolved pollutant. For colloid, we are using the settling approach, and for the dissolved, we are using again decay rate, and at the end we calculate the design. We design the green infrastructure and size of the GI. We have a cost module, which is a last module, and the cost is calculated based on the GI value. The core of GIP-SWMM is an optimization procedure that integrates flow and pollutant loads from a SWMM model, and also uses the target water quality and quantity as constraints, and a set of green infrastructures and their performance and their costs, and finally selects the efficient combination and distribution of GIs over the watershed. So let's go to our case study. The case study we have in this tool, it's a mid-Hawthorne drainage basin, which is located on the eastern part of the Rapid City, South Dakota. And it drains approximately 8.5 square kilometers. And it has 35 sub-basins as shown in the figure. We have some output of from GIP-SWMM. Here is the discharge and TSS removal based on the cost, and we have also the two types of bacteria, E. coli and fecal coliform reduction based on the cost. And we have the distribution of the green infrastructures and the numbers in different sub-basins as it's shown based on that. For example, for a sub-basin with higher peak flow, the tool prefer to put and place the GI in those type of sub-basins. And also same scenario for the pollutant removal. Conclusion, so we have a significant merit of GIP-SWMM is that we translated complex approaches to easy to use, computationally less intensive, but it's still rigorous physically based module that could be verified with observation. The limitation of this tool is because we made some assumptions for simplification during the developing process. GIP-SWMM may not be as accurate as complex tools. And the application of this tool is GIP-SWMM can aid decision makers in analyzing various stormwater scenarios at the watershed scale in the short period of time. And this is a paper we submitted in Journal of Environmental Management. Thank you very much for listening to this presentation.